So we would want to find out the how the transmitter of MSK would be implemented, and the first thing is to look at the equation that represents an MSK signal. And as we have seen in our previous video, we have seen that we divide the signal into in-phase and quadrature component. We have seen that the quadrature component is delayed by t bits, by t bit duration, and for us to be able to generate the continuous wave, we require a slow wave or a slow signal whose frequency is omega b over 4. So how do we get that? We know it's 2 pi fb divided by 4t. When you perform this evaluation, you find that this is equivalent to pi t over 2 tb. What we know for sure is that fb is equivalent to 1 over tb. So we can present it as such or as a reciprocal of tb. So this is the slow moving signal that is going to be used to modulate our fast moving carrier frequency with 2 pi fc, so that after we have been able to generate the in-phase component, then we are going to be able to generate our carrier signal when of course combined with the quadrature component that is generated with the delay of tb. So if we come back here, we had looked at this. So what we are doing is that we have our bit stream right here, our bit stream right here, and it is divided into the odd bits and even bits. And then we have our slow moving waves with the omega bt over 4, and the other one is phase shifted by 90 degrees to become a sine with the same frequency of omega b over 4. Then you multiply these two with the even and odd bits. We see now they are forming discontinuities, as you can see, as you saw in the previous lecture. That is, they are discontinuities. But for us now to be able to do that, we must have our, for us now to get this, we are going now to use the equation that we have just seen right here. And what we know for sure is that cos A cos B gives us cos A plus B plus cos A minus B. So if our A is our high frequency component and our B is our low frequency, is our omega B over 4 component, then we can be sure that when you have this component, this might be used to represent the one symbol A, one symbol 1, and the lower frequency, that is A minus B, can be used to represent the zero symbol. So for that reason, we are going now to look at how we can achieve that. And there are a number of ways in which we can have a transmitter or modulator of MSK. One method is displayed right here, whereby the first step is we have from our message signal. From our message signal, we take it through a serial to parallel converter. And what that does is to split the in-phase from the quadrature component. So we have I of t and q of t. So those are the bits, the odd bits and even bits. So the even bits are then taken through the encoder, NRZ encoder or bipolar NRZ encoder to generate now a signal that has positive voltage for symbol 1 and negative voltage for symbol 0. This signal is multiplied at the more balanced modulator with this sine wave that has frequency of omega b over 4, just like we have seen, so that we are able to form I of t sine omega b t over 4. This is what we have here at the output of the first modulator. We have another local oscillator that generates a high frequency carrier signal with the frequency of omega c of t with amplitude A, and then we multiply this in-phase component with the high frequency carrier to form the modulation, And what we observe from that point is that we are now able to generate cos A, cos B, like we have already seen. And this is now a combination of cos of A plus B and cos of A minus B. Bottom or at this lower section, we have our even bits. They are taken through the NRZ encoder to give us positive going pulses for symbol 1 and negative going pulses for symbol 0. Then they are delayed with by a delay function, and therefore we are able to obtain Q of T minus TB. Therefore the bits or the signals will be lagging by 1 bit duration. And then just like we were able to obtain the sine omega b over 4t, similarly we can have the pi shifted version, pi over 2 shifted version of that signal, so that it's now a cosine function. What we are simply saying is that sine omega b t over 4 plus pi over 2 is equivalent to cosine of omega b t over 4. So this is the pi shifting that we are talking about. Therefore, when we now multiply this, we have Q of T minus TB multiplied with cos omega b t over 4. So similarly, just like we had the local oscillator generate our carrier signal here, when it is pi over 2 shifted, it becomes a sine function, and you multiply now with our delayed baseband signal, that is B bipolar NRZ encoded, and multiplied with our omega b over 4 signal, we are able to obtain this signal that can be considered to be the quadrature component of our MSK signal. It is now equivalent to Q T minus TB cos omega b over 4 T cos omega c T. And again, following this idea of cos A cos B takes the form of cos A plus B plus cos of A minus B. If these ones are divided by 2, the amplitude doesn't affect us much, can be considered to be a constant K. So when we have these two now, they are added together at this point, then we have our MSK signal generated as such. There is another method in which we can be able to generate our MSK signal. It is not very different from what we have just shown. The idea is that we are getting an MSK signal that is a product of cosine, or 2 cosines. This is our omega b t over 4, and this is our omega c. And similarly with the other one, this is omega b t over 4, this is omega c. So the only difference is the period. As you can see, one is the 1 period per height. So this one starts at 0. This one starts 1 period area. So clearly we can see that the second quadrature function is delayed by 1 TB. For that reason, when we do that, we are able to generate our MSK signal in a similar manner.